Hello everyone, my name is Dr. Manish Taunk, Associate Professor of Physics, School of Basic and Applied Sciences, Maharaja Agrasen University, Himachal Pradesh. Today I am taking this session on crystal imperfections. But before starting on crystal imperfections, I will briefly discuss about the classifications of materials and specifically the crystalline materials. As we know, the materials are generally classified into crystalline, polycrystalline, and amorphous materials on the basis of their structure. In crystalline materials, they are further categorized into single crystals. As you can see in this slide, the single crystal material, polycrystalline material, and amorphous materials are shown. So, what are single crystals? Single crystals have a periodic atomic structure across its whole volume. At long-range length scales, each atom is related to each other equivalent atom in the structure by translational or rotational symmetry. As you can see in this picture, single crystal has a definite pattern of atoms throughout its edges. The atomic arrangement or the pattern of the atoms remains throughout same in a single crystal. As you can see in this diagram, a real single pyrite crystal is shown here. Now come to the polycrystalline solids. Polycrystalline materials are made up of an aggregate of many small single crystals, or they are also called as crystallites or grains. Polycrystalline materials have a high degree of order over many atomic and molecular dimensions. Now, what are grains or domains? These grains and domains are separated by grain boundaries. The atomic order can vary from one domain to the next. That means, as you can see in this diagram, the arrangement in this domain, arrangement of atoms in this domain is different from the arrangement of atoms in this domain, and which is different from the neighboring domain. So, in short, polycrystalline contains multiple arrangement of atoms and molecules, but that arrangement continues to a shorter length and then another arrangement of the atom initiates. So a polycrystalline material in short contain many crystalline domains. The grains are usually 100 nanometer to 100 micrometers in diameter. Polycrystals with grains less than 10 nanometer in diameter are known as nanocrystalline. Now let's come to the amorphous solids. Amorphous or non-crystalline solids are made up of randomly oriented atoms, ions, or molecules that do not form a defined pattern or lattice structure. In other words, we can say the atoms and the arrangement of atoms or molecules in amorphous material is very short range. Amorphous materials have order only within a few atomic and molecular dimensions. Amorphous material do not have any long range order, but they have varying degrees of short range order. Examples of amorphous materials include amorphous silicon, plastics, glasses. Amorphous silicon can be used in solar cells and thin film transistors. You can see the arrangement of atoms in the amorphous material. So amorphous material don't have any particular shape or pattern. Now let's come to the crystal lattice. A crystal lattice is defined as an infinite array of points in space where each point has identical surrounding to all others. And these arrays are arranged in a periodic manner. Suppose, as you can see in this diagram, this origin point O and A has a uh, distance of A, small a. This small a distance continues from in this line for next atom to atom arrangements. So that means after every distance of A, an atom has been placed. Similarly, from O to B, the distance is B. So in this direction, after every distance of B, there is another atom placed in this particular direction. So this is the crystal lattice where a regular or periodic arrangement of atoms is maintained. Now, crystal structure. Crystal structure can be obtained by attaching atoms, group of atoms or molecules which are called bases to the lattice sides of the lattice point. So crystal structure is a combination of crystal lattice and bases. As you can see in this diagram, if crystal lattice is combined with the bases, which is atoms or group of atoms, then it forms the crystal structure. Now come to the unit cell. The unit cell is the basic building block of any crystalline material. And in this unit cell, for example, you can see in this diagram there are three axes x, y, and z. Along x-axis, the length of the unit cell is A. Along y-axis, the length of the unit cell is B, and along z-axis, the length is C. So this A, B, C are three length parameters. And similarly, the angle parameters are alpha between B and C, the beta, and the gamma. So combinedly, these three dimensional parameters and three angular parameters forms the six lattice parameters of any unit cell. Only 1/8 of each lattice point in a unit cell can actually be assigned to that cell. Each unit cell in the figure can be associated with one lattice point. So three common unit cells in three dimensions are simple cubic, the body-centered cubic, and the face-centered cubic. In simple cubic, you can see that each corner is occupied by the atom. In a simple cubic, there are 8 corners and each corner is occupied by an atom. In the body-centered cubic, in addition to each corner, one atom is also placed at the center of the unit cell. So this is known as the body-centered cubic. In face-centered cubic, in addition to each corner, every face of the unit cell. That means there are 6 faces in this unit cell. So every face of the unit cell is occupied by an atom. So based upon these three-dimensional unit cells, there are 7 crystal classes. And these 7 crystal classes are identified on the basis of values of their lattice parameters, that is ABC and alpha, beta, gamma. So there is a cubic class, there is tetragonal, there is orthorhombic, hexagonal, monoclinic, triclinic, trigonal. These are the 7 crystal classes. Now let's come to the imperfections in crystals. So imperfections in crystals are intentional or unintentional. By the meaning of intentional imperfections, intentional imperfections are created depending upon the requirement of certain properties. For example, in case of semiconductors, when we dope a material with N-type or P-type impurities, that is to enhance the specific properties like electrical conductivity. In case of to enhance the electrical conductivity, we dope the material. So in that category, the imperfections are intentional. And sometimes when we need a pure material, even then, without any doping, the imperfections are present in the crystal during their growth process. So it is almost impossible to avoid all the imperfections during the crystal growth. The crystalline imperfections can be classified on the basis of their geometry as follows. Crystal imperfections or defects are categorized into point defects, line defects, surface defects, and volume defects. The point defects are further categorized into vacancies, interstitial vacancies, compositional defects, which is further categorized into substitutional impurity and interstitial impurity, and the electronic impurity. The line defects are categorized into two types: edge dislocation and the screw dislocation. Surface defects. These are categorized into three categories: grain boundaries, twin boundaries, and the tilt boundaries, and stacking faults. Volume defects. Volume defects are uh, the non-crystalline regions of dimensions at least 10 to 30 angstrom. These are known as volume defects. So now we will discuss every category one by one. So the first is point defects, or they are also known as the zero-dimensional defects. Under point defects, first imperfection is the vacancy. The vacancy refers to an atomic site from where the atom is missing. As you can see in this picture, an atom has been missing from its lattice site. So as the atom is missing, it create a void here. Now the neighboring atoms of this vacancy are slightly pushed toward the center of this vacancy, like this atom, this, and this. These four atoms have been slightly pushed toward the center of the vacancy, and their alignment is slightly different from their neighboring other atoms. So this type of defect is known as the vacancy, and because of this vacancy, a tensile stress is created around this vacancy, which creates the distortion of the plane. Now the another point defect is substitutional impurity. A substitutional impurity refers to a foreign atom that has replaced the parent atom. Now, as you can see in this picture, a parent atom which is of the larger size as compared to the a substitutional impurity which is of the larger size as compared to the parent atom is placed in this lattice site. So because of the larger size, this substitutional impurity has pushed the neighboring atom toward outside. So their center is slightly shifted outwards, and it has created a compressive stress field in the atoms surrounding this impurity. Similarly, in the next picture, as you can see, impurity atom is placed, but it is of the smaller size than the parent atom. So, due to its smaller size, it gets fitted into this lattice site, and the neighboring atoms are slightly pushed toward its center, which created a tensile stress around this impurity. So this type of substitutional impurity is there in crystals. Now the next is the interstitial impurity. An interstitial impurity refers to small sized atoms occupying the void space in the parent crystal without replacing the parent atoms. As you can see, a impurity which is placed in the interstitial site. If it is of the same size as the void space is there, it will not create any compressive or tensile stress. But if it is of the if it is placed within the void space and displaces the atomic arrangement, then it will create the compressive stress field. Now, next is the Frenkel imperfection. An ion displaced from a regular site to an interstitial site is called Frenkel imperfection. As you can see in this picture, an atom is shifted its position from its regular site to the interstitial site. So this type of defect or impurity in the crystalline material is known as the Frenkel imperfection. Now the Schottky imperfection, a pair of cation and anion missing from an ionic crystal resulting in a pair of vacant ion sites, is known as Schottky imperfection. As you can see, an atom has been missing from this place and another atom is missing from this place. So anion and cation both are missing from this crystal structure, forming the Schottky imperfection. Now the last among the point defects is electronic defects. Electronic defect occurs because of the errors in charge distribution in the solid. These defects are produced when the composition of an ionic crystal does not correspond to the exact stoichiometric formula. As you can see,